Hi, this is Sam Ziss from Professor Uselin's Thermodynamics class. Today I'm going to be working through a problem from Chapter 3 of our textbook. This is problem 3-29. I'm going to start by reading the question. It says a piston cylinder device contains 0.85 kilograms of refrigerant 134A at negative 10 degrees Celsius. The piston is free to move has a mass of 12 kilograms and a diameter of 25 centimeters. The local atmospheric pressure is 88 kilopascals. Heat is transferred to the 134A until the temperature is 15 degrees Celsius. We need to determine the final pressure, the change in the volume of the cylinder, and the change in the enthalpy of the refrigerant. So just jotting down what we have the mass of the refrigerant equals 0.85 kilograms. The mass of the piston is 12 kilograms. The atmospheric pressure was given as 88 kilopascals. The diameter of the piston was 25 centimeters. I'll go ahead and convert that to meters. That's 0.25 meters. The initial temperature was negative 10 degrees Celsius, and the final temperature was 15 degrees Celsius. Our first job is to find the final pressure, P2. It's actually going to be the case for this problem that the initial pressure will be equal to the final pressure, and we can find that by adding the atmospheric pressure to the pressure caused by the piston. If we kind of think of this as a free body diagram, here's our cylinder. You have the atmospheric pressure coming down, and you also have the pressure from the piston coming down. To get the pressure from the piston, we're going to go ahead and multiply the mass of the piston times gravity and divide that by the area of the piston. The way that we get this formula is that the numerator there, mass times gravity, will get us a weight. We're dividing by area because because pressure is defined as a force over an area. So plugging in, we were given that the atmospheric pressure was 88 kilopascals. Plus the mass of the piston was given as 12 kilograms. We'll take gravity to be 9.81 meters per second squared, divided by, we know that this is the area that we're finding is for a circle because we were told that it has a diameter. So we'll find the area of this circle with pi over 4 times our diameter, which was 0.25 meters squared. And when we calculate this, we get that the initial pressure, which is equal to the final pressure, is 90.4 kilopascals. While I've got this number handy, later on we're going to need to convert this to megapascals. If we divide this by 1,000, we will get 0.0904 megapascals. We'll come back to that later. The second part of this question asks for the change in the volume, so that is what we will go after next. Part B tells us to find the change in the volume. And before we can go after this, we need to make a decision about whether this material is saturated or superheated. And we can make that decision using table A12, where we can take a look at Sorry, we're not on to table A12 yet. Let me come back to that in just a second. What we're going to look at is this diagram that we've looked at in class before, where we relate our temperature to either our specific volume or the internal energy or our internal enthalpy. This is the shape that we look at for any of these graphs, with mixtures falling under this dome. And the piece that I'm going to focus on here is right here with the saturation temperature. And the number that we're going to be looking at here is for 90 kilopascals. And this is where table A12 comes in. When we are at 90 kilopascals, the temperature that we're going to be looking at for saturation is negative 28.65. And what we're seeing is that our temperature is of either negative 10 or 15, our initial or our final temperatures are greater than that saturation temperature, which we can see from our table for 90 kilopascals is negative 28.65 degrees Celsius. And since our temperature is greater than the saturation temperature, we know that our substance is superheated. Since it is superheated, we then turn our attention to table A13. Again, the reason that I know it's A13 is because that is for superheated refrigerant 134A. So our goal right now is to find the change in the volume. In order to do that, we are going to need our specific volume at a temperature of negative 10 degrees. But we run into a little bit of a problem with the pressure. Again, the pressure that we're working with is 0.0904 megapascals. But I don't exactly see those pressures. I do see 0.06 and I do see 0.10. Our pressure falls between those two pressures, which means that we will need linear interpolation. We've gone through a lot of linear interpolation examples in class, including some of the other videos that I posted. I'm not going to go ahead and calculate the specific volumes using linear interpolation. I'll just describe it. We're going to be using this value right here as well as this one for both negative 10 degrees and for 15 degrees. And we are going to find that for state 1, the specific volume is 0.242 meters cubed per kilogram. For state 2, the specific volume is 0.2544 meters cubed per kilogram, so that we can then go get the change in the volume by subtracting V2 minus V1, but notice that these V values that I have here are specific volumes, so we will just multiply our mass across there. And when we plug all of those in, we are going to get that our change in volume is 0.0105 meters cubed. That ends part B. The last piece that we need to get back to the problem statement was the change in the enthalpy. That's also going to be using linear interpolation. It's just that the values that we're going to be looking at are under this H column here. So we will go through that process of linear interpolation for both -10 degrees Celsius and for 15 degrees Celsius. So similarly to the change in the volume, the change in the enthalpy will be H2 minus H1. So we will multiply our mass across the specific enthalpies. And when we finally go get that final answer, we will find that the change in our enthalpy will be 17.4 kilojoules. Thank you very much for watching.